Chapter 6, Iterative Reconstruction Basics. The filtered back projection has several limitations, including image noise and the creation of artifacts. While the noise issue can be overcome by increasing the MAs or the milliamperage, then this increases the dose, which presents a real challenge, especially in our dose-conscious CT environment right now. This is even harder to achieve in low-dose CT exams in an effort to adhere to the ALARA principles. In a perfect world, the filtered back projection would work out just great, even with assumptions made regarding the algorithm that is used for it. In order to derive the filtered back algorithm, the following assumptions must be made. First, the X-ray focal spot is a point source. This is the first assumption. Second, the size and shape of each detector cell is not taken into consideration. Third assumption is that all X-ray photon interactions are assumed to take place at a point located at the geometric center of each detector cell, not across the full area of the detector cell, but at simply the center. The fourth assumption is that a pencil beam is used to represent the line integral of the attenuation coefficient along the path. The next assumption that must be made is that the size and shape of the voxels are described as an infinitely small point located on a square grid. The sixth assumption is that the projection data are accurate and that they are not affected by the X-ray photon statistical changes and the electrical noise. Figure 6.2 in your book lays out these assumptions. So, as we all know, using a reduction in dose is a huge goal in modern CT today. As we use low-dose techniques, these scans can produce noisy images, which are unacceptable to the rads. So these four techniques include projection space denoising, analytical FBP, remember filtered back projection, denoising, using the standard reconstruction kernels, image space denoising, and the use of iterative image reconstruction. Image space denoising and the FBP-based analytic reconstruction use digital filters. For example, smoothing and edge enhancement filters. Projection space denoising, which is filtering before image reconstruction, uses photon statistics to reduce noise through a statistical noise model or adaptive noise filtering. The IR reconstruction, or the iterative reconstruction algorithms, have been put in place to reduce image noise when using low-dose CT techniques, which allow for the low dose and also still the preservation of the image quality. And also this reduces artifacts from metal objects, beam hardening effects, and from photon starvation. Remember, these artifacts show up more when using the filtered back projection algorithm, and there are several iterative reconstruction algorithms available from the CT scanner manufacturers today, and the book has actually placed these into three categories, which are iterative methods without remodeling, statistical methods with modeling of photon counting statistics, and model-based methods that exceed statistical modeling. So of the several IR algorithms that are available from the CT scanner manufacturers that the book has placed into the three different categories that we just noted on the last slide, we will first discuss IR algorithms without modeling. To begin, you need to know that a typical iterative reconstruction process consists of three steps: input, the IR loop, or the iterative reconstruction loop, and the output. We will begin by talking about the input. Here, the scanner produces raw data, or measured projection data. The FBP algorithm is applied to this raw data in order to generate the initial CT image. With the iterative reconstruction loop, the forward projection is applied to the initial CT image to create the artificial raw data. This is also called simulated projection data. Then, the simulated projection data is compared with the measured projection raw data. The difference is then calculated to produce the updated image, and this difference is known as the correction term. The difference between the two shows the amount of adjustment or update needed for the current estimation of the image. The goal here is to keep the difference between the two as low as possible. You don't want it to be very high at all. The updated image then is back projected using the FBP algorithm to the current CT image. That then brings us to the output. The output of the IR loop is a back projection that results in the final volumetric image. This whole process may seem a little hard to grasp and mind-boggling, but please refer to page 119 in your book for an excellent illustration and layout of the process, and this can be seen in figure 6.4. Modeling approaches in IR algorithms. The term modeling is used to refer to the characteristics of the CT imaging system and the imaged object, and it includes what has been popularly referred to as system optics, also known as the optics model, which addresses the X-ray source, the image voxel, and the detectors. The noise model addresses the X-ray photon statistics, which are the X-ray flux at the source and at the detector. The object model then deals with the radiation attenuation through the patient, and the physics model examines the physics of the CT data acquisition. I want to point out that the system optics, or the optics model, affects image quality improvement, and the noise statistics, the objects model, and the physics model affects reduced dose, better low contrast detectability, and also artifact reduction. Statistical methods with modeling use X-ray photons during the IR process. So the iterative statistical reconstruction algorithms can operate in the projection raw data domain, in the image domain, and during the process of iterative reconstruction itself. Model-based methods try to model the acquisition process as accurately and as closely as possible. As I've noted before, there are lots of iterative reconstruction algorithms currently available from the CT manufacturers on the market, such as GE, Siemens, Philips, and Toshiba. Each vendor offers algorithms that provide image quality and noise reduction in low-dose CT imaging compared with the FBP algorithm. You can refer to Table 6.1 for examples of all these algorithms that are offered by the different manufacturers. So we will discuss a few of them right now. In 2008, the first IR algorithm was commercially available, and this is called the ACER. Then other algorithms were developed, which you can see in Table 6.1 in your book. We're going to focus on just these two, the ACER V, which is GE's next generation of ACER, and the ADER 3D, which is from Toshiba. With the ACER V, this features sophisticated noise modeling and object modeling, including a bit of physics modeling. But this does not focus on system optics modeling. This results in faster image reconstruction, similar to filtered back projection. Another advantage of the ACER reconstruction is that it can be used with low-dose CT exams and delivers a lower radiation dose to patients. It reduces streaks and noise and improves spatial reconstruction when compared with the FBP algorithm for equivalent image noise. The ADER 3D algorithm is from Toshiba and operates in both the raw data and the reconstruction domains, and is based on the scanner model that models the physical properties of the CT imaging system and a statistical noise model examining both quantum and electronic noise in the raw data. The ADER 3D reconstruction increases the signal to the noise ratio, which then improves spatial resolution and produces images that look more natural. An important step in the need for IR algorithms is the need for performance evaluation of algorithms in CT. These performance evaluation studies are based on both phantom and on patient models. So in 2012, Studies were published comparing the performance of the ACER algorithm with the filtered back projection algorithm, and there was a 26 to 30% reduction in image noise seen. Even more astonishingly, the dose reduction of 46.4% for chest CTs and 38.2% for abdominal CTs was seen. The ACER images had much less noise than the filtered back projection images did. In 2013, studies were done and compared with the filtered back projection algorithm with the ACER and the model-based IR algorithms using the standard and low dose techniques for chest CT exams. The results showed that the model-based IR algorithms, or the MBIR algorithms, produced significant noise reduction in the low dose CT scans. Continuing on, in 2014, there were studies done that compared the performance of the ADER 3D algorithm with the FBP algorithm regarding noise reduction and image quality improvements. The results showed that the ADER 3D was effective in noise reduction and the image quality improvement when compared with the filtered back projection algorithm. This also showed that the ADER 3D had high effectiveness, and it can increase as the phantom size increases, meaning the patient size as well. And then in 2015, studies were done that compared the performance of a knowledge-based iterative model reconstruction algorithm, the IMR, from Philips with the filtered back projection algorithm at a standard dose on lesion detection, at a reduced dose in abdominal CT scans, and performance on image quality. These results show that all true lesions on the standard dose FBP images were detected on the reduced dose IMR images across all the patients studied. So I know that going over the examples from 2012 to 2015 may be a little confusing, but I just wanted you to see how the performance of the IR algorithms really affects the images and also the other areas in CT that are focused on today, such as noise and dose to the patient.